Welcome back. Now, what about f double prime? That is the second derivative. Okay, this is an important feature as well. Now, you have two functions. They are both increasing. Notice this is also increasing, so is this. What is the difference between the left and the right here? This is called concave up. Okay, the curvature is looking up, right? So this is called concave up, whereas this is called concave down. Okay, so again, this is called concave up, this is called concave down. What's the difference between these two is the following. Maybe the next graph, next picture will tell you. This is concave up. Look at the tangent here. Looks like the slope is, well, not very high. Maybe 0.1, 0.5. Here it may be 1. Here it may be 2. In other words, the slope increases. So notice concave up, the slope itself is increasing. Here is concave down. Here it is very steep. Here the slope is less steep. Here the slope is even less steep. So in concave down, the slope decreases. All right. In concave up, the slope increases. In concave down, the slope decreases. All right. If the graph of f lies above all its tangents, then it is called concave up. If the graph of f lies below all its tangents, it is called concave down. Okay? The graph f is above all the tangents. The graph g is below all the tangents. How can you possibly draw a tangent inside? It will cut. The tangent here has to be drawn above. The tangent here has to be drawn above, so on. Likewise, this one, the tangent has to be drawn below, not above, has to be drawn below. So when the curve f, graph of f is above the tangents, it's concave up. It's same as saying slopes increase. Here, the curve G is below all the tangents, so the slopes are decreasing. This is concave down. All right. Here, you are concave down starting from here to here. Concave down. You are concave up from B to C. Concave down from C to D. Concave up. There is no slope here, mind you. There is no slope here. That is, these are pointed points, okay? Regardless, concave up in between. Concave up here, concave down here. All right. The second derivative helps determine intervals of concavity. All right. Slope of my curve is less. Slope of my curve is a little higher. Slope of my curve is even higher. That gives me concave up. That is f double prime is positive because slope is increasing. F double prime positive is concave up. When f double prime is negative, slope is decreasing. Slope decreases. F double prime negative. That makes it concave down. Okay, which brings us to the concavity test. If f double prime is greater than 0 in an interval I, then the graph of f is concave up. on I. If f double prime is less than 0 for all x in your interval I, then the graph of f is concave down on I. Okay, this is concavity test. Okay. For example, where do you think is the curve concave up? 0 to 12, it's concave up. From 12 onwards, it becomes concave down. All right. So 0 to 12, and then 12 onwards, it's concave down. Okay, which brings us to inflection point. A point P on a curve is called an inflection point if f is continuous and the curve changes from concave up to concave down or from concave down to concave up. So inflection point is where concavity changes. All right, let's go to this curve. At 12, notice concavity changed. To the left, it was concave up. To the right, it is concave down. So that point is called inflection point. Okay? Inflection point. I will stop my slide here. I'll continue from the second derivative test. Until then.